Irwan. I am from PT PJB UP Brantas. For this time, I will present about my presentation study on the PV system development at UP Brantas for hydroelectric power plant station service supply. Here we go. PT PJB UP Brantas managed 13 hydropower plant spread over 5 districts at East Java with a total installed capacity about 291 megawatt, consists of annual and daily reservoir types. Daily reservoir or KTH has the potential to develop a PV system as floating installation type. Tailrace area has the potential to develop PV system as both floating and canal top installation type. There are two kinds of station service supply for hydropower, type 1 and type 2. This is type 1 and type 2. In type 1, when the generator in operation, electrical energy flow from generator to the PLN grid and load center, and type 2, when generator in operation, electrical energy flow from generator to PLN grid, load center separate from the PLN grid. In type 1, import energy record when the generator stop in operation, so the load center supply from the PLN grid. In type 2, import energy record when the generator stop or in operation, so the load center supply from the PLN grid continuously. This is a PV system for station service supply in type 1 and type 2. This is a PV system. This picture describe about the PV system supplies electricity for the hydropower station service. With the PV system, the load center is supplied continuously without depending on imported energy. Generator production is not reduced due to station service needs, and the PV system would be installed in a hybrid configuration. This flowchart shows us about methodology for the study. The study starts by determine location PV system to estimate PV energy, and then we compare between PV energy and energy consumption. If the PV energy greater than energy consumption, so the PV system is sufficient for station service supply hydropower. And then we estimate LCOE. LCOE compared with the reference tariff. If LCOE value cheaper than reference tariff, so the study is accepted to implement. Reference tariff is 0.172 refers to PT PLN Board of Director regulation. This table shows us about potential location for PV system. So we have 9 location, 9 potential location for PV system. It is name of location, and then area, potential area, and then installation type, estimated area, and energy consumption for each hydropower. The picture Seguro hydropower in this location, potential location, potential area, Mendalan hydropower in this picture, and Sutami hydropower this picture. PV system energy estimate determined using the PV module specification according to the table. Nominal power is 320 watt peak, and sun hours approximately 5 hours. From the module specification, we can calculate the estimate power. So, by the module specification and estimated area, we can calculate the estimate power for PV system in every hydropower. This table informs about minimum land requirement and PV system capacity for station service supply is from the estimated area and estimate power. We can calculate the minimum land requirement. So from this table, it has enough land to develop PV plant in KTH and tailrace for station service supply. And then we calculate using LCOE using simulation by system advisor model. I use financial assumption according to the table. So we get the result in table right hand. We use 3 system simulation, PV system simulation, and then PV plus storage. There is capital cost storage is 700, and PV plus storage there is storage capital cost is $1,600 per kilowatt. There is some of alternative case. So this is and there is range of capital cost in every system simulation. So from the financial assumption and then capital cost, range of capital cost, we can calculate LCOE value. This value, and then we compare LCOE value with tariff tolerance. So we get the deviation of LCOE and tariff tolerance. From the table, inform that the development of a PV plant in UP Brantas to meet the needs of hydropower station service supply is feasible to be implemented. So the positive value of deviation, it's mean feasible PV to be implemented. Conclusion number 1, development of a PV plant to meet UP Brantas hydropower station service is very potential and realistically implemented. Number 2, UP Brantas has enough land to develop PV system in KTH and tailrace for station service supply. Number 3, most of the average cost of developing a PV plant using both battery energy storage and without energy storage, battery energy storage, is still feasible to be implemented. Number 4, PV power plant is carried out using a hybrid decentralized grid-connected system configuration in the hydroelectric power plant load center bus. Thank you for your attention and see you next time.